Now that we've understood the guiding principle, the A intersection B, which is equal to B intersection A, we are going to be proving the formula. We're going to prove the formula using this guiding principle. So we are saying that if A intersection B is equal to B intersection A as explained by this diagram right here, it means that all the places in the main formula, let me just start again. We are starting again. Okay. So now we are going to be going on to the proving of the Bayes theorem using the probability tree. So now we are going to be looking at the formulas that we derived from the main tree. We're going to look at how to use the guiding principle to prove Bayes theorem on the probability tree. Okay, so we know already that A intersection B is equal to B intersection A, because for an intersection, no matter how you switch it around, the intersection points will always be the same. Okay. So we're going to be looking at the first formula we got from the main tree, which is the probability of A. And we said the probability of A is equal to the probability of A intersection B plus the probability of A intersection not B. Okay. So we are saying that can be, its direct reverse is going to be the probability of B intersection A plus the probability of not B intersection A. The direct reverses of probability of A and B is going to be probability of B and A, and probability of A and not B is going to be not B and A. So we are going to break down these expressions using the probability tree, the reverse tree, and that's how we got this expression. So from the reverse tree, we can see the probability of A given B times the probability of B is equal to the probability of B intersection A. And the probability of A given not B times the probability of not B is equal to the probability of not B intersection A. So we are going to put these or fit these expressions into the equation, and that's how we come up with our equation number 1. The probability of not A again. So when we are looking at, is the second formula we're going to be looking at. So the probability of not A, which is given to us by the main tree as the probability of not A intersection B plus the probability of not A intersection not B. Its direct reverse, or the direct reverses of these intersection points, are going to be the probability of B intersection not A plus the probability of not B intersection not A. Again, we look at the reverse tree to find the breakdown of these expressions, and we fit them into the formula, and that's how we come up with our equation number 2. So that's going to be a probability of not A given B times the probability of B plus the probability of not A given not B times the probability of not B. Now we come to our third equation, which is the probability of B given A. That's given to us as, like in the original tree or the main tree, as probability of A intersection B over the probability of A. Here, let's note this. The probability of A intersection B is going to be a probability of B intersection A. But the probability of A here is not going to be the probability of B. The probability of B is not a direct reverse of the probability of A. So we are going to look at our equation 1, where we broke the intersection points, which is the probability of A and B being probability of B and A, and probability of A and not B being probability of B, not B and A. So we are going to use that, find these expressions on the reverse tree, and fit them into the equation. So the probability of B and A is going to be a probability of A given B times the probability of B, all over the probability of A given B times the probability of B plus the probability of not A given not B times the probability of not B. And this is how we come up with our third equation. Now we move on to our fourth equation, which is the probability of not B given A. That, again, from the main tree would be given to us as the probability of A intersection not B over the probability of A. Now direct reverse again of the probability of A and not B, A intersection not B or A and not B, is going to be probability of not B intersection A. And the probability of A, we break that down using the main tree, probability of A intersection B plus the probability of A intersection not B. And we find the direct reverses of that, as you can see here. We find the expressions that break them down and we fit them into the equation. Okay. We do the same thing for equation number 5, which is going to be the probability of B giving not A and the probability of not A, which is given to us as the probability of not A intersection B over the probability of not A. Now, as we did for all the earlier formulas, we'll look at the direct reverses of these, which is the probability of not A intersection B, which will be given to us by the reverse tree as the probability of B intersection not A. The probability of not A, we break it down again using the formula from the main tree, probability of not A intersection B, and the probability of not A intersection not B. Find the direct reverses of that, which would be probability of B and not A and probability of not B and not A. We find the breakdown of those expressions in the reverse tree, fit them into the equation, and we'll get our equation number 5. Next would be our last equation, probability of not B given not A, which is given to us on the main tree as the probability of not A intersection not B over the probability of not A. Direct reverses, as we've done for earlier formulas, will be the probability of not B intersection not A all over again. The probability of not A would not be probability, this direct reverse will not be the probability of not B. This direct reverse is going to be the breakdown of the intersection points. We find that equation, find the direct reverses of those equations as we've done earlier for equation number 2. And then as we get the breakdown or the reverses of those expressions, we find the breakdown in the reverse tree and fit them into our equation and get our equation number 6. I hope this sheds light on the proving of Bayes' theorem on the probability tree, and this clears up any confusions that may come up.